66 million years ago, in what is now Montana, a massive three-horned giant grazed peacefully on ancient ferns and cycads. This creature, weighing as much as an elephant and armed with horns longer than baseball bats, had no idea it was about to witness the most catastrophic event in Earth's history. Above the prehistoric landscape, a rock the size of a mountain hurtled through space at unimaginable speed. In just a few moments, this cosmic visitor would transform our planet forever, ending the reign of the dinosaurs and paving the way for mammals to inherit the Earth. But here's the mystery that has captivated scientists for decades. Did this space rock really kill the mighty Triceratops, or is there more to this ancient story than we've been told? The evidence we've uncovered will shock you, and by the end of this investigation, you'll understand why this single moment in time changed everything we know about life on our planet. Welcome to the most incredible detective story in paleontology, where cosmic forces collide with Earth's mightiest creatures. This isn't just about dinosaurs. This is about understanding how a single day 66 million years ago shaped the world we live in today. The story begins in a place that might surprise you. Not in some exotic jungle or remote desert, but in the Badlands of Montana at a formation geologists call Hell Creek. This isn't just any fossil site. This is ground zero for understanding the final chapter of the dinosaur age. Picture this landscape 66 million years ago. Massive rivers meandered through lush forests, filled with flowering plants that had just begun to dominate the Earth. The climate was warm and humid, more like modern-day Florida than the harsh winters Montana experiences today. And roaming through this prehistoric paradise were some of the most magnificent creatures ever to walk our planet. Triceratops ruled this ancient world like no other herbivore before or since. Standing 10 feet tall and stretching 30 feet from nose to tail, these giants were perfectly engineered for survival. Their massive skulls, some measuring over 7 feet long, supported 3 deadly horns and a bony frill that could deflect the attacks of even the fearsome Tyrannosaurus rex. But Triceratops wasn't just big, it was incredibly successful. Fossil evidence reveals that these 3-horned titans made up nearly half of all large dinosaurs living in North America during the final million years of the Cretaceous period. They had evolved complex dental batteries with hundreds of sharp teeth that could slice through the toughest vegetation. Their powerful jaws could process plants that other herbivores couldn't even touch. These weren't primitive creatures stumbling toward extinction. These were highly evolved animals at the peak of their evolutionary success, thriving in vast herds across the western interior of North America. Some scientists estimate that Triceratops represented 5/6 of the large dinosaur population at the end of the Cretaceous period. And they weren't alone in their success. The Hell Creek ecosystem supported an incredible diversity of life. Tyrannosaurus rex, the apex predator, stalked through forests hunting the massive duck-billed Edmontosaurus. Armored Ankylosaurus, built like living tanks, browsed on low-growing plants. Swift Ornithomimus raced across open plains on powerful legs designed for speed. This was no dying world. This was a thriving, complex ecosystem that had been stable for millions of years. Food was abundant, diversity was at its peak, and dinosaurs showed no signs of gradual decline. In fact, many species were still evolving and adapting right up until the very end. But high above this prehistoric paradise, something was approaching that would change everything. Racing through the cold vacuum of space at over 55,000 miles per hour was a carbonaceous asteroid more than 6 miles wide. This wasn't just any space rock. This was a cosmic missile loaded with enough energy to reshape continents. Recent groundbreaking research has revealed the shocking origin of this celestial destroyer. Using advanced geochemical analysis, scientists have traced this asteroid's birthplace to the outer reaches of our solar system, far beyond the orbit of Jupiter. This discovery is revolutionary because it means the object that ended the age of dinosaurs came from the frozen depths of space, carrying with it materials that had remained unchanged since the solar system's formation. The asteroid's journey to Earth began millions of years earlier, when gravitational forces nudged it from its distant orbit. Like a cosmic pinball, it ricocheted through the solar system, pulled by the gravity of planets and moons, until it found itself on a collision course with our blue world. As it approached Earth's atmosphere, the asteroid began to heat up from friction with air molecules. But unlike smaller meteors that burn up completely, this mountain-sized projectile was far too massive to be stopped by our planet's thin atmospheric shield. Instead, it plunged through the air like a bullet through tissue paper, its surface glowing white-hot as it screamed toward the shallow seas off what is now Mexico's Yucatan Peninsula. The impact site couldn't have been worse for life on Earth. The Yucatan region was covered by shallow tropical seas, rich in sulfur-bearing rocks. When the asteroid struck, it didn't just create a massive explosion, it vaporized billions of tons of these sulfur-rich sediments, launching them high into the atmosphere where they would wreak havoc on the global climate. In the first microseconds after impact, temperatures at ground zero exceeded those found in the core of the Sun. Rock, water, and asteroid material were instantly vaporized and blasted outward at speeds that defied comprehension. The explosion created a crater more than 120 miles wide and 12 miles deep, gouging a wound in Earth's crust that can still be detected today. But the initial blast was just the beginning. Within minutes, massive chunks of molten rock were raining down across North America. These impact spherules, some as large as marbles, fell like deadly hail across the Hell Creek region, where our Triceratops herds grazed peacefully just moments before. The evidence for this cosmic catastrophe is written in stone. At sites across Montana, paleontologists have discovered a thin layer of clay that marks the exact moment when the asteroid struck. This boundary layer contains concentrations of iridium, a metal extremely rare in Earth's crust, but common in asteroids, that are thousands of times higher than normal background levels. Even more remarkably, scientists have found tiny glass spheres within this boundary layer, created when the impact blast melted rock and hurled it hundreds of miles through the air before it cooled and fell back to Earth. These spherules provide a smoking gun that links the Hell Creek dinosaurs directly to the Chicxulub impact. But here's where our detective story takes a fascinating turn. Recent excavations have uncovered Triceratops fossils just inches below this boundary layer. These aren't ancient bones from millions of years before the impact. These are the remains of dinosaurs that were alive when the asteroid struck, perhaps even witness to the first moments of the catastrophe that would end their world. One particular discovery has revolutionized our understanding of the extinction timeline. In Montana's Hell Creek Formation, researchers found the horn of a Triceratops embedded in rock just 5 inches below the impact boundary. This fossil represents what may have been the very last dinosaur on Earth, a creature that lived and died at the exact moment when 66 million years ago, years of dinosaur dominance came to an abrupt end. The precision of this timing destroys earlier theories that dinosaurs were already in decline before the asteroid arrived. Instead, it paints a picture of thriving ecosystems suddenly and catastrophically disrupted by forces beyond anything these creatures had ever experienced. The environmental chaos that followed the impact unfolded like a nightmare beyond imagination. Within hours, massive tsunamis generated by the asteroid strike began racing across ancient seas, carrying debris and destruction thousands of miles from ground zero. These weren't ordinary waves. These were walls of water hundreds of feet high, moving faster than jet planes and capable of scouring entire landscapes down to bedrock. But the tsunamis were just the opening act in a planetary disaster that would unfold over months and years. As billions of tons of vaporized rock and sulfur compounds shot into the upper atmosphere, they began to spread around the globe like a deadly blanket. The sky itself became Earth's enemy, blocking out the sun and plunging the planet into an artificial winter that would last for nearly 2 years. Imagine the terror of those final Triceratops herds as their world transformed before their eyes. The familiar warmth of the Cretaceous sun disappeared behind a veil of impact debris and sulfuric aerosols. Temperatures that had remained stable for millions of years began plummeting toward freezing. The lush forests that had fed countless generations of plant-eating giants started withering and dying as photosynthesis ground to a halt across vast regions of the planet. Recent scientific modeling reveals the horrifying precision of this environmental collapse. The impact released approximately 67 billion tons of sulfur into the atmosphere, creating acid rain that fell across continents for months after the initial strike. This wasn't gentle precipitation. This was caustic rainfall that could strip leaves from trees and poison the very water sources that surviving animals desperately needed. The darkness was perhaps the most devastating aspect of the post-impact world. For creatures that had evolved under bright Cretaceous skies, the sudden onset of perpetual twilight triggered a cascade of ecological disasters. Plants that had supported massive food webs for millions of years began dying en masse. The complex dental batteries that made Triceratops so successful at processing tough vegetation became useless when there was simply nothing left to eat. But some species faced an even more immediate threat. The impact debris raining down from the sky wasn't just rock and dust. Much of this material was superheated, glowing like embers as it fell back to Earth. Forests across North America erupted into massive wildfires as this molten rain ignited vegetation that had already been stressed by the initial shockwave. The Hell Creek region, once a paradise of diverse plant life, became a hellscape of smoke, fire, and falling ash. The fossil record from this period tells a story of unimaginable suffering. At sites across Montana and the Dakotas, paleontologists have discovered mass death assemblages where multiple species died together in what appears to be a single catastrophic event. These aren't gradual extinctions spread across thousands of years. These are snapshots of ecosystems collapsing in real time. One of the most haunting discoveries comes from the Tanis site in North Dakota, where researchers have uncovered what appears to be a fossilized moment, frozen in time. Here, fish with impact spherules still lodged in their gills lie buried alongside fragments of dinosaur bones, amber containing microscopic debris from the impact, and plant material showing clear evidence of sudden, violent death. This site may preserve the actual day the asteroid struck, capturing the first hours of the extinction in extraordinary detail. The evidence suggests that many dinosaurs didn't die immediately from the impact itself, but rather from the gradual breakdown of their ecosystem over the following months and years. For large herbivores like Triceratops, this slow starvation may have been the cruelest fate of all. These giants required massive amounts of vegetation daily to fuel their enormous bodies. As plant communities collapsed, even the most successful dinosaur species found themselves facing an impossible mathematical equation. There simply wasn't enough food left on Earth to sustain populations of such large animals. The size threshold for survival became brutally apparent as the impact winter deepened. Scientific analysis shows that virtually all land animals weighing more than 55 pounds went extinct during this period. This weight limit wasn't arbitrary. It represented the maximum size that Earth's devastated ecosystems could support during the years of darkness and cold that followed the impact. Adult Triceratops, weighing between 12 and 16,000 pounds, were doomed by their very success. The same massive size that had made them dominant herbivores for millions of years now sealed their fate. Smaller animals could survive on seeds, insects, and carrion, but nothing in the post-impact world could sustain creatures that needed hundreds of pounds of fresh vegetation every day. Yet, The extinction wasn't uniform across all species. Birds, the direct descendants of dinosaurs, managed to survive the catastrophe in remarkable numbers. Small mammals, having spent millions of years living in the shadows of giant reptiles, suddenly found themselves inheriting a devastated but empty world. These survivors possessed crucial advantages that the mighty dinosaurs lacked. They could shelter in burrows, survive on limited food sources, and maintain their body temperature even as global temperatures plummeted. The speed of the extinction challenges everything we thought we knew about how species respond to environmental change. Evolution typically operates over millions of years, allowing organisms to gradually adapt to changing conditions. But the Chicxulub impact compressed millions of years of environmental change into a few catastrophic months. No amount of evolutionary adaptation could have prepared Earth's creatures for such rapid and complete ecosystem collapse. Modern climate modelling reveals that the impact winter following Chicxulub was more severe than nuclear winter scenarios that terrified scientists during the Cold War. Global temperatures may have dropped by as much as 50 degrees Fahrenheit in some regions, turning tropical paradises into frozen wastelands virtually overnight. For cold-blooded reptiles like dinosaurs, such temperature swings represented an impossible physiological challenge. The chemical signature of this ancient disaster can still be detected in rock layers around the world, providing a permanent record of Earth's darkest hour. The boundary clay that marks the end of the Cretaceous period contains not just elevated levels of iridium, but also shocked quartz crystals that form only under the extreme pressures generated by asteroid impacts or nuclear explosions. These microscopic time capsules preserve evidence of forces so powerful they literally change the atomic structure of rock. But perhaps the most remarkable aspect of this cosmic catastrophe is what it reveals about the fragility of even the most successful ecosystems. The Hell Creek Formation shows us a world at its evolutionary peak, teeming with diverse and highly adapted species that had thrived for millions of years. Yet within a geological instant, this entire world vanished, leaving behind only scattered bones and the testimony of rock layers to tell its story. The aftermath of the Chicxulub impact created a world that would have been completely unrecognizable to any surviving Triceratops. As the initial fires died down and the tsunamis receded, what emerged was a planet transformed beyond comprehension. The familiar landscapes that had supported dinosaur civilizations for over 160 million years had been erased, replaced by a toxic wasteland where survival became a daily battle against impossible odds. Recent drilling projects into the Chicxulub crater have revealed shocking details about the first minutes after impact. Scientists discovered that the asteroid didn't just create an explosion, it literally turned solid rock into vapor, launching granite from deep within Earth's crust hundreds of miles into the atmosphere within minutes of the strike. This wasn't destruction on a local scale. This was planetary surgery performed with cosmic precision. The sulfur compounds released during the impact created a particularly insidious form of environmental poisoning. Unlike the dramatic explosions and fires that marked the first days after impact, sulfuric acid aerosols worked their deadly magic slowly and invisibly. These microscopic particles spread throughout Earth's atmosphere like an invisible plague, turning ordinary rainfall into chemical warfare against every living thing on the planet's surface. For plant-eating giants like Triceratops, this acid rain represented a double catastrophe. Not only did it directly damage the vegetation they depended on for survival, but it also leached vital nutrients from soil that had taken millions of years to develop. Even if plants could somehow survive the darkness and cold, the very ground they grew in was being systematically poisoned by chemistry that fell from the sky. The Hell Creek ecosystem had been a masterpiece of evolutionary engineering, with intricate food webs connecting hundreds of species in complex relationships that had been refined over geological ages. Triceratops didn't exist in isolation. These giants were keystone species whose grazing patterns shaped entire plant communities, whose massive herds created migration routes used by smaller animals, and whose very presence influenced the behavior of predators and prey across thousands of square miles. When Triceratops populations began to collapse, the ripple effects cascaded through every level of the ecosystem. The flowering plants that had co-evolved with dinosaur herbivores suddenly found themselves without their primary pollinators and seed dispersers. Predators like Tyrannosaurus rex, perfectly adapted to hunt giant herbivores, faced starvation as their prey disappeared. Even the smallest creatures felt the impact, as decomposing dinosaur carcasses temporarily enriched some areas, while leaving vast regions completely barren. But here's what makes this extinction truly extraordinary. The fossil evidence shows that many dinosaur species were still actively evolving right up until the moment of impact. Triceratops itself underwent significant morphological changes during the final 2 million years before extinction, developing new horn configurations and frill decorations that suggest ongoing evolutionary pressures and adaptations. This wasn't a group of evolutionary relics struggling to keep up with changing times. These were dynamic, successful species actively responding to their environment and continuing to diversify. The two recognized species of Triceratops, T. horridus and T. prorsus, show clear evolutionary progression through the Hell Creek Formation, with younger rocks containing specimens that display measurably different characteristics from their ancestors. The discovery of juvenile Triceratops fossils just below the impact boundary provides another piece of this tragic puzzle. These young dinosaurs represent the future that never came to pass. They were growing up in stable family groups, learning to navigate their complex social structures, and preparing to continue evolutionary lineages that stretch back over 100 million years. The asteroid didn't just kill individual animals, it erased potential futures that can barely we imagine. Modern paleontologists have developed sophisticated techniques for understanding how these final dinosaur communities functioned. Analysis of bone chemistry reveals details about diet, migration patterns, and even social behavior that paint an increasingly complex picture of late Cretaceous life. Triceratops herds weren't just random aggregations of animals. They were sophisticated societies with age-structured groups, seasonal migration patterns, and complex communication systems that allowed them to coordinate movements across vast territories. The preservation of soft tissue impressions in some Hell Creek fossils has revolutionized our understanding of what these creatures actually looked like in life. Far from the drab reptilian monsters of popular imagination, many dinosaurs displayed vibrant colors and intricate patterns that served for species recognition, mate selection, and camouflage. Triceratops frills may have been adorned with bright displays that could change color based on mood or social context. These behavioral complexities make the extinction even more poignant. When the last Triceratops died, Earth lost not just a species, but an entire culture that had developed over millions of years of evolution. The social knowledge, migration routes, and behavioral adaptations that had allowed these animals to thrive across an entire continent vanished forever, leaving behind only scattered bones to hint at the richness of what was lost. The speed of the extinction also reveals something profound about the relationship between Earth and space. Our planet exists within a cosmic shooting gallery where asteroids and comets regularly cross orbital paths with potentially devastating consequences. The Chicxulub impactor had been traveling through the solar system for millions of years before its fateful encounter with Earth, following gravitational influences that we're only beginning to understand. What makes this particular impact so remarkable is its almost perfect timing for maximum biological devastation. Had the asteroid struck during a different geological period, when life was less diverse or more dispersed, the extinction might have been less severe. But 66 million years ago, Earth was experiencing one of the most biodiverse periods in its history, with complex ecosystems packed with large, specialized species that had little resilience against rapid environmental change. The asteroid's composition also played a crucial role in the severity of the extinction. As a carbonaceous chondrite from the outer solar system, it contained high concentrations of volatile compounds that vaporized upon impact, contributing to the atmospheric disruption that proved so deadly to large animals. A different type of asteroid might have caused less atmospheric damage and allowed more species to survive the initial impact. Recent computer simulations have revealed the terrifying precision of the Chicxulub impact's destructive power. The angle of impact, approximately 60 degrees from horizontal, was nearly optimal for launching debris into the atmosphere while minimizing the amount of material that escaped Earth's gravitational field entirely. A steeper or shallower impact might have been less catastrophic, but the actual trajectory maximized both immediate destruction and long-term environmental effects. The global nature of the extinction becomes clear when we examine fossil sites around the world. From Mongolia to Madagascar, from Argentina to Alaska, the same pattern emerges. Thriving dinosaur communities suddenly vanish from the fossil record at exactly the same geological moment, replaced by the characteristic boundary clay that marks the impact event. This synchronicity across continents provides overwhelming evidence that a single catastrophic event, rather than gradual environmental change, caused the extinction. Yet even as we understand more about how the extinction unfolded, new mysteries continue to emerge. Some dinosaur lineages appear to have been more vulnerable than others, with plant-eaters like Triceratops suffering disproportionately compared to some smaller predatory species. The reasons for these differential survival rates remain hotly debated among paleontologists, with theories ranging from metabolic differences to behavioral adaptations. The story of Triceratops and the Chicxulub impact also illuminates the role of pure chance in shaping the history of life on Earth. If the asteroid had missed our planet by just a few thousand miles, or if it had struck a few million years earlier or later, the entire trajectory of evolution would have been different. The age of mammals might never have begun, and intelligence as we know it might never have evolved. This cosmic lottery has profound implications for understanding life in the universe. The development of complex ecosystems like those preserved in the Hell Creek Formation requires not just the right planetary conditions, but also the absence of catastrophic interruptions. The rarity of large impact events in Earth's recent history may be one of the key factors that allowed intelligence to evolve, suggesting that complex life might be far more fragile and uncommon in the cosmos than we previously imagined. The extinction boundary also represents one of the most dramatic examples of punctuated equilibrium in the fossil record. For millions of years, dinosaur evolution proceeded through gradual changes and adaptive radiations. Then, in what amounts to an instant in geological time, entire lineages that had dominated terrestrial ecosystems simply disappeared, replaced by completely different groups of organisms that had previously lived in ecological margins. This pattern of sudden, catastrophic change, followed by rapid evolutionary innovation challenges traditional views of how evolution operates. The mammals that inherited the post-impact world didn't gradually outcompete dinosaurs through superior adaptations. Instead, they survived an environmental catastrophe that their reptilian contemporaries could not, then rapidly diversified to fill empty ecological niches in a world suddenly free of giant predators and competitors. The chemical and physical evidence for the impact continues to accumulate as new analytical techniques are developed. Researchers have found microscopic diamonds formed under the extreme pressures of impact, exotic amino acids that could only form under conditions present during the collision, and magnetic anomalies that record the incredible forces unleashed when asteroid met Earth. Each new discovery adds another piece to the puzzle of understanding how a single day changed the course of life on our planet. Perhaps most remarkably, we're now finding evidence that some effects of the Chicxulub impact persisted for hundreds of thousands of years after the initial collision. Sediment cores from around the world show that ecosystems didn't simply bounce back once the impact winter ended. Instead, recovery was a slow, complex process that involved the gradual rebuilding of soil communities, the evolution of new plant associations, and the establishment of entirely different predator-prey relationships. The legacy of that ancient catastrophe continues to shape our world today. The mammals that survived the extinction event were the ancestors of every mammalian species, now plants that manage living, including ourselves. The flowering to persist through the environmental chaos gave rise to the diverse flora that now covers our planet. Even the bacteria and fungi that decomposed the massive amounts of organic matter left behind by the extinction played crucial roles in recycling nutrients and preparing the ground for new evolutionary experiments. So there you have it. The Meteor mystery has been solved, and the answer is both simpler and more profound than anyone could have imagined. Yes, that cosmic visitor from beyond Jupiter's orbit did indeed kill Triceratops, but it did so much more than that. It ended an entire world. The evidence is overwhelming and undeniable. From the iridium-rich boundary clay to the Triceratops horn found just inches below the impact layer, science has painted a crystal-clear picture of the last day of the dinosaur age. These magnificent three-horned giants weren't struggling evolutionary failures. They were thriving, successful, and still evolving right up until the moment a mountain-sized asteroid turned their paradise into a toxic wasteland. What happened 66 million years ago wasn't just an extinction. It was a cosmic reset button that erased 165 million years of dinosaur dominance and handed the keys to Earth's future to small, furry creatures hiding in burrows. Without that asteroid, there might never have been mammals large enough to evolve intelligence. There might never have been humans to ask these questions or tell these stories. The fragility of life, the power of chance, and the incredible detective work of modern paleontology have given us this remarkable window into our planet's most dramatic chapter. Every time you see a bird flying overhead, remember that you're looking at the last living dinosaurs, the sole survivors of that ancient catastrophe.